This is Learning Assessment Problem 225. The goal of this problem is to calculate the value of the voltage V sub O appearing across a 12K resistor. In the next chapter, you will learn techniques for solving this problem more directly, but at the moment, the tools that we have available are Ohm's law, the two Kirchhoff's laws, current division, and voltage division. In order to calculate that voltage V sub O, we'll probably have to know something about the current flowing through that resistor. Unfortunately, at the moment in this circuit, there are no simple ways to reduce the combinations of resistors. That is, there are no series or parallel combinations which would enable us to proceed with the solution. So the problem-solving strategy here is to consider the use of a Y to delta or delta to Y transformation of the resistor circuit. If we look at this enlarged view of the circuit and consider the possible Y's and delta configurations, we have a delta in this upper mesh, a delta in the lower mesh, and wherever we have three resistors tied to a node, that would form a potential Y connection. We've labeled the nodes A, B, C, and D, and notice that the voltage which we'd like to determine, this V sub O, is the node voltage VBD. And it will be important in whatever transformations we perform that we maintain those two nodes B and D in the circuit so that we can eventually predict that voltage difference. So let's label some resistor values, R1, R2, and R3. This is the delta configuration portion of the transformation. I'm going to transform to the Y circuit, and again the nodes A, B, and C are the same as those in the delta configuration, but now we've inserted the equivalent Y trio of resistors, RA, RB, and RC. And notice that we've developed an additional node E here in this process of transformation. So we'll consider the calculation of those equivalent Now we'll consider the calculation of the resistor elements in the equivalent Y circuit. We have the resistor R sub A is equal to R1 times R2 divided by the sum of the resistances in the delta configuration. And that will be equal to 12K times 12K divided by 12K plus 12K plus 12K, and that is equal to 4K. Because of the equality of the resistor values in that delta configuration, the 12 kiloohms all around the triangle there, we'll have that RB is equal to RC is equal to RA, and that's equal to 4K also. So now we'll see what we've accomplished by doing this transformation. Here we have the circuit with the resistors RA, RC, and RB installed. Let's rename some resistances RSC and RSB. These are series combinations where RSB is equal to 4K plus 12K, and that's equal to 16K. And similarly, RSC is equal to 4K plus 12K equals 16K. Now we'll consider the process of current division. Recall that we're trying to determine the voltage V sub O or VBD in this circuit. And if we could determine the current flowing down through there, we'll name it I sub O. We could use Ohm's law to predict the voltage V sub O. We have a current source of 4 milliamps, so we have 4 milliamps flowing down node A to node E, and then that current will divide in these two parallel branches. So by current division, we can say that I sub O is equal to 4 milliamps times the resistance in the other parallel branch, which is RSC, divided by the sums of the two parallel branch resistances, RSB plus RSC. That's equal to 4 milliamps times 16K divided by 16K plus 16K. And that's equal to 1/2 times 4 milliamps. Or we have that I sub O is equal to 2 milliamps. And now we're in a position to calculate V sub O. V sub O will equal I sub O times 12K. That will equal 2 milliamps times 12K. Or V sub O is equal to 24 volts. If we go back to the original circuit and look at the values of resistors, it probably, with a little imagination, be obvious that this voltage of 24 volts could be readily predicted because of the very symmetric nature of the values of the components. But we'll let that be your pondering.